Alright, welcome back everybody. In this video we're going to talk about information related to section 10.4 of AP Calculus BC, the integral test for convergence. Alright, so what we're going to do in this lesson, we're going to introduce you to the integral test for convergence. Then we're going to do a few examples where we focus on making sure that the conditions for the integral test are met. We can only apply this test in given situations, and to apply it in a situation where it doesn't work would be totally inappropriate and would lead us to some wrong conclusions. We're going to talk about why the integral test works the way that it does, and then we're going to use it to determine if a few series converge or diverge. Okay, so here we go, the integral test for convergence. If f is a positive, continuous, and decreasing function for x greater than or equal to m, where m is some positive integer greater than or equal to 1, and a sub n can be expressed as a function f of x, then the sum from 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or they both diverge. And so this gives us a double-edged mechanism for showing whether or not a series converges, or similarly for showing if an integral converges. If we have a series that we're trying to decide whether it converges or not, we can utilize this test and try to find the value of the series as an integral in order to show that the series converges based off of the integral converging or diverging, either way. And you'll see this in some of the later examples probably in our next video. But this connection exists between the two where either both converge or both diverge. And so if we want to find whether this series converges or diverges, and we're capable of finding whether this integral converges or diverges, we can use the behavior of this integral to determine the behavior of this series, and vice versa. This is not one of my favorite tests, but it does help us in a few situations. And so, we're going to carry on and take a look at it. Here we go. Example 1. Determine whether the following series meet the conditions of the integral test. Okay, what are the conditions of the integral test? Well, the function has to be positive, it has to be continuous, and it has to be decreasing for all values of x greater than or equal to m. Okay, so here we go with the first one. The sum from 1 to infinity of 2n over n squared plus 1. So the first thing we want to do is we want to verify, is 2n over n squared plus 1 positive? For given n values. And I can tell pretty easily that this one is positive for n values greater than or equal to 1, because the denominator here is always positive. N squared plus 1 is always positive. And when n is greater than or equal to 1, the numerator is also positive. So when we take a positive divided by a positive, it indeed gives us a positive value. So we've verified that this is positive. We met the first condition. Second condition, continuous. All right. If you think about the function 2n over n squared plus 1, this is continuous. How can I tell? Well, because there are no discontinuities. But the way that I can easily tell that there are no discontinuities is the fact that this denominator is always defined. N squared plus 1 never equals 0. And so we never have a division by 0, which is the only, given a function of this form, is the only possible type of discontinuity, and therefore we know that this function is continuous. So we've met the first two conditions. The third condition, we need to make sure that it is decreasing. Now sometimes it's pretty easy for you to just look at a sub n and tell whether or not it's decreasing. But it's going to be more beneficial for us a lot of times if we can't easily tell from glance whether or not it's decreasing. Well, how do we decide if a function's decreasing? If you think about the answer to that question, you should, dig back, way back into Calc AB and think about, oh yeah, a function's decreasing when its derivative is negative. So the easy way to show that this function is decreasing is by showing that this expression, its derivative, is negative. So I'm going to go ahead and take the derivative of this. And in order to take the derivative of this, we're going to use the quotient rule. So we've got low times the derivative of high minus high times the derivative of low. Square the bottom. And away we go. All right, and simplifying this algebraically, that gives us 2n squared plus 2 minus 4n squared all over n squared plus 1, the quantity squared. So that gives us 2 minus 2n squared all over n squared plus 1, quantity squared. And now you should recognize that this derivative, the denominator is always positive for any value of n, and the numerator is going to be negative for any value of n greater than 1. All right? Therefore, this decreases for n greater than or equal to 1. And so we've met all three conditions for the first part of this example. All right, let's go ahead and look at part B of this example. All right, so looking at example B, we're going to go back through and look at this series and whether it meets the same three conditions. So you go ahead and start with, is it always positive? And we're looking at the sum from 3 to infinity here. So we really are only concerned with it being positive from 3 to infinity. Well, if you think about this, the square root always outputs a positive value. For n greater than or equal to 3, this is always going to be a positive value. And for all values of n, the numerator is going to be positive. So we're good there. This is going to be positive for all n greater than or equal to 3. So it meets that characteristic. It's positive. All right, now, as far as continuity goes, the only values of n that are concerning for us in this denominator here are values of n that are smaller than 3. So again, we're looking at this and saying, hey, this statement, it is continuous for n greater than or equal to 3 because all discontinuities are at n values less than 3. Continuities are for n less than 3. And then the last part, again, we're going to try and see, is this decreasing for all of these values? So again, we're going to have to start by taking the derivative of this, since it's not something that I would say is obvious whether it's decreasing or not. So we want to take the derivative of this expression and see if it's positive or negative. We want it to be negative for all these n values in order for it to be decreasing. So we're going to go ahead and take that derivative. So we've got low d high, so 3 minus 7 to the 1/2 times 1 minus n times 1/2 times 3n minus 7 to the negative 1/2 times 3, and square the bottom. Gives us 3n minus 7 as our denominator here. And so simplifying, this gives us 3n minus 7 to the 1/2 minus 3/2 n times 3n minus 7 to the negative 1/2 all over 3n minus 7. If we multiply everything by 3n minus 7 to the 1/2 to clear out the negative exponent, it gives us the quantity 3n minus 7 minus 3/2 n all over the quantity 3n minus 7 to the 3/2. And so we're looking for, is this positive or negative for n greater than or equal to 3? The denominator is always positive for those n values So we're looking at the numerator. What happens when n is greater than or equal to 3? If we simplify this even more, this is 3/2 n minus 7. And you'll find that while this is negative for 3, and it looks like it's negative for 4, but once n gets to be 5, this numerator is going to be positive, and the denominator is positive. And so what we've got here is for n greater than or equal to 5, this is positive. So the series is increasing. Therefore, the integral test does not apply. Okay, so that takes us to the end of this example, and we'll make that the end of this video. We'll come back next time and we'll talk about why the integral test works the way that it does, and also a few examples where we actually use the integral test to determine the divergence or convergence of some of our infinite series. All right, see you next time. Bye-bye.